All right, so we did the definition. So far we've done the definition of the sources, and we've also talked about KVL and KCL. But now what we are going to do, we are going to continue our discussion, and we are going to go into resistance and Ohm's law. Now, let's take a little bit of a deeper look at what that means, both from a physical standpoint and from a mathematical standpoint. Again, I'd like to make this distinction because it's important to understand what is physics, what's mathematics, because it can lead to the confusions that we saw, for example, before when you had two ideal voltage sources attached in parallel with different values and things of that sort, where a mathematical abstraction starts failing. So we are talking about resistance and Ohm's law, or resistance, let's say first. So the first question is, what is resistance? What is the meaning of resistance? Now we have that we've defined voltages and currents and things of that sort. Now think about it from a physical standpoint. You can have a slab of material, right? You can have something that looks like this. So let's say it's a rectangular slab. Mine doesn't look like one, very clear. But anyway, use your powers of imagination to get it. So let's say it's a slab. It has a cross-section area of A, a length of L, and it's made out of some material. So the question is, what is resistance? Where does that come from, right? Now, we know something. I mean, all of you probably know that you can define a quantity. So what they teach the first pass is that for regular resistors, you have a voltage that's proportional to the current, or current that's proportional to the voltage. And they even tell you what is the resistance. They say, well, the resistance, which basically in this case is going to be the relationship between the V and I, you can write this R times I, is for the slab is, what is it? It's proportional to what? If you make this twice as long, would the resistance increase or decrease? You will get more resistance or less resistance? More resistance. So it has to be proportional to L. It has to be, how about the cross section? If I put two of them in parallel, side by side, do I see less resistance or more resistance? I make less resistance. I'm making a larger pipe. The first one is a longer pipe, if you want to use the hydraulic analogy. This one is a wider pulp, a thicker pipe, right? And then that proportionality constant is called rho, resistivity, which has units of ohms times meter. But this is meter squared. And ohms, of course, has units of volts per amps. And we know what volts and amps are already. So that's the basic kind of a high-level view of a resistance. But why is that so? Why is it that the current is proportional to the voltage? It's actually quite subtle. Let me ask you this. What is the thing that carries the current? Electrons or electric charge, yes, correct, electrons. Let's say electrons. Now, if I had a little box that's basically emptied of anything, it's just basically vacuum. And if I have an electron here, and if I apply, so let's say I have two electrodes, and apply a voltage across these two. So let's say I apply some sort of a voltage here, like that. What happens with the electron? Starts moving. More precisely, in mathematical or in physical terms, it starts accelerating. Right? What determines that acceleration? The electric field. What laws of physics you can use? I mean, very basic stuff. What law of physics determines the rate of acceleration? The force, Newton's second law, right? F equals ma. So let's say it has also a mass, which it does. And F is what? The electric field times the charge, right? In this case, it's negative charge, so it becomes like that. So A essentially becomes proportional to negative E over m E in vacuum for an electron. Right? Is this constant current? No, right? Everyone's shaking their head, right? What is it? It's constant. What is constant current? What quantity, what mechanical quantity or kinematic quantity needs to be constant for this to be constant current? Velocity. However, we see, and we know the electric field is related to the voltage, right? So the electric field times this length is the voltage. So we know that this is E times well, L is going to be V. But now it seems like your acceleration is really proportional to the electric field or voltage. While if you wanted to get constant current, you should have had a velocity that's proportional to that. That's what I said. It looks simple, but it's subtle, actually. That can't be the picture. The difference is that, yes, if you had vacuum, then it doesn't look like a resistor. It's not a linear resistor at all. But a slab of, let's say, copper, a slab of some material, a slab of graphite, does more or less behave linearly. So what's happening? Say again? Why?
Because you have all sorts of electrons moving in random directions, so if you add up all of them, then...
You're saying that you have whole sorts of electrons moving in random directions, so if you add them up, you may get something else, which is actually quite relevant and close to the truth, yes.
There's also like a terminal velocity because there's like some resistance to flow, like just a line.
You say there's a terminal velocity. Okay, that's also another way to think about it. So, yes, Will.
Propagation of the electrons, because when one electron starts moving, it pushes the other ones down.
Okay, propagation. So you're saying that they are pushing each other. Okay, that's also another interesting hypothesis. Yeah.
Well, the electrons might be scattering off the atoms.
Scattering off of the atoms, right? There are big atoms. And so let me ask you a question. The electrons inside this piece of copper, let's say I take a piece of copper, I should have probably brought a piece of copper with me. Look at the electrons inside that copper. Do they move fast, or very slow? How many people think they're moving very slow? And how many people think they are moving very fast? Okay. All right. Interesting. So let me show you two things. You're in a way both right. But by the same token, your both groups are having an incomplete picture, let's say. So let me run so what determines the speed of an electron? What makes electrons move inside a piece of copper, first of all? If I have just like a solid piece of copper, why are these electrons moving to begin with? Yeah. Thermal motion, right? So if there's thermal energy. Now there's something in physics, basically you may have not seen it already, or you may have. It's called equipartition theorem from the kinetics. So basically it says that in thermal equilibrium, when things are in thermal equilibrium, every degree of freedom takes, on the average, 1/2 of kT. K, Boltzmann constant, 1.38 10 to the minus 23 joules per Kelvin. T is the temperature in absolute terms in Kelvin. That each degree of freedom takes that much. In other words, if I have a pendulum hanging here in this room, it's vibrating slowly, and in x direction, the energy of it is on average 1/2 of kT. In y direction, is also its energy is 1/2 of kT. Now, so what is the kinetic energy? So I'm going to make a simplistic calculation. There are some assumptions here you can understand. So I have a 1/2 v squared, 1/2 mv squared. This is the kinetic energy of an electron, right? M is the mass of the electron. What's the mass of the electron? Okay, good. Negative. So you see, I see a lot of people talking about the 9 or 9.1, but they may not remember the exponent. If you want to remember one thing, remember the exponent. Because the maximum error you can get by not remembering that first part is a factor of 10. If you miss a single number in the exponent, you are already a factor of 10 off. So to me, if I want to do it quickly, instead of saying 9.1 10 to the minus 31, I say basically 10 to the minus 30 kilograms. Okay, if I want to do back of envelope calculations in my head, say that's 10 to the minus 30. Electron charge is 10 to the minus 19. Boltzmann constant is 10 to the minus 23. KT at room temperature is 410 to the minus 21. That's enough for me. I'm not very precise in those. I mean, because it doesn't matter because there's a whole bunch of other assumptions that have led into this. But anyway, so that, and how many degrees of freedom does an electron in free space have? 3, exactly. In other words, how many numbers do you need to specify to tell me where it is? X and Y and Z, right? 3. So it's a 3/2 of kT. So if I calculate this, okay, so let's get rid of these. And again, there's some assumption here about root mean square average, and there are different kinds of average, but it doesn't. KT at room temperature, we said is 4, 10 to the minus 21 joules. So that's times 3, that's 1.2, 10 to the minus 20. I really should drop this, but I will just keep it. And this is 9.1, let's say just 10. 10 to the minus 30, let's get rid of that. So I'm going to make this approximately 10 to the minus 20, 10 to the minus 30, v squared. So v squared is roughly 10 to the minus, 10 to the plus 10, right? Meter squared squared. So v is approximately 10 to the 5 meters per second. Again, if you want to convert it to kilometers per hour times 3.6, so that's 3.6, 10 to the minus, 10 to the 5 kilometers per hour, or you can convert it to miles per hour, if that gives you a better sense. That's going to be roughly around 200,000 miles per hour. That's not too slow. That's pretty darn fast. The electrons inside that piece of copper are moving on average with this speed. Right? That's the random thermal movement. They're going all over the place. They're going crazy. You just don't see it. Right? Think about how long will it take for them to get from one end of it to the other end if they were going with that speed without hitting anything. Take them very, very short period of time. Yeah.
The question I have is, the electrons are detached from their respective copper atoms?
Right. These are basically ionized. These are. Otherwise, you wouldn't get conduction. Right? That's what makes the difference between a conductor and an insulator. In an insulator, at room temperature, you don't have enough energy to release these electrons. So those electrons are tightly bound. Diamond, for example, right? I mean, or glass. You can release those electrons, but the energy it takes is more than what you get from average thermal energy.
It's not just copper, it's conducting copper.
Yes, it's copper at room temperature, which would be conductive copper. Copper at different temperatures will behave differently. I mean, there are other things. Copper can become also superconductor. That's a completely different phenomenon at very low temperatures. But the electrons, they're free electrons. Let's put it this way. So what happens is that these electrons are going crazy all over the place. Right? So, but this is only half of the story. So as you can imagine, when they are going around this quickly, they're constantly colliding with the lattice, with the atoms that are sitting there, the big ions that are sitting there, constantly scattered, as was mentioned right earlier. So there's this whole bunch of electrons and massive electrons that are going around and doing this thing, forming this cloud, this crazy cloud, right? But it's just staying within that thing. Now that's in the absence of an electric field. When you apply electric field, what happens is that, yes, in between these collisions, they feel a little bit of an electric field and start moving a little bit, changing their velocity vector a little bit, accelerating, meaning that the velocity vector gets a small component added due to the electric field. But as soon as they hit something, that gets randomized. They bounce around, they go in a different direction, so that energy is not even, that velocity is not even pointing, that component of the velocity is not pointing in that direction. So since they're very frequently colliding with the lattice, they don't get time to accumulate this velocity. It just constantly gets randomized. And that's why this cloud of electrons starts moving as you apply electric field. You can think about the center of gravity of this cloud of electrons moving, or center of charge more accurately. Center of charge of this thing will move. But now, how quickly does that movement happen? So let's talk about that. So think about the cloud. Right? How many electrons are there? Let's say I'm carrying a current of, 1 amp within this piece of copper. 1 amp is not a low current. It's not a huge current. It's not a low current. So you have 1 amp of current flowing through this piece of copper. Right? How much movement is that? So let's say how many electrons are there in a piece of copper? So copper, atomic number is 29. I think atomic mass is 64 or something. So let's say I have 64, to make my life easier, right? Let's say I have 64 grams of copper. So let's say this slab is exactly 64 grams, which would be 1 mole of copper. Let's say there's one free electron for copper. It's not exactly correct, but let's just make things like this. How many electrons is that? How many free electrons are in that slab? If it's 1 mole of copper and there's 1 electron per atom. What's a mole? If you want to remember one number. 6 10 to the minus, 6 10 to the 23, right? Avogadro's number. If you want to remember one number in science, one number, it should be Avogadro's number. That's, I think, the most important number. Because it captures so many important fundamental things. The things are made of atoms and things of that sort. But anyway, so that one you may want to remember the 6.02, 10 to the negative 23, 10 to the 23, not negative 23. Yes, there would be 1 out of in a mole. No, 10 to the 23 atoms per mole. So that's about 10 to the 23 electrons, right? Roughly. So let's say 10 to the 23 electrons inside that thing. Free electrons, not electrons. There are other bounded electrons. There's a lot more electrons, but just those are the ones that can move around. Okay? So now if I want to carry, if these electrons move, if all of these electrons are displaced in 1 second, how many, so basically let's say the length of this, whatever it is, let's say the length of this is 1 meter. Make this simple. So these electrons are displaced in 1 second. That would be 1 meter per second average velocity. How much current is that? So we're talking about the displacement of the center of charge of this electronic cloud that's going crazy, right? So what's that current? Well, we know the charge of the electron, right? So this times 1.6 10 to the minus 19 coulombs per electron. Electrons cancel. So this is basically the I. So 1.6 times 6 is 10, okay, roughly. So that's 10 to the 24, 10 to the 19, so that's 10 to the 5 amps. So if they were to move at 1 meter per second, that would correspond to 10 kiloamps. So we said this was 1 amp, so the speed of that movement of that center of charge of that for I equals 1 amp corresponds to an average speed of 10 to the minus 5 meters per second. That's that very slow that some of you pointed out. And that's that very fast. They're two different things. This is called drift velocity. Later on you will hear it. That's the thermal velocity. They're two different things. So if you were to explain this to your younger brother or sister or your younger niece or nephew who's in middle school, high school, very interested in science, they say, well, you know what? You look at this piece of copper, you know, this is not fancy, but you know how fast electrons are going inside it. They could go around the planet if they go at this speed, you know, 10 times, you know, in 1 second and things like that, and they would just, wow, amazed. You know, those are the things that sometimes we miss. People don't get excited about these things. They should be, because they don't see it. Now, here's the thing. How do you explain it to them without writing these equations, without telling them equipartition theorem, you know, something like that? Why are these electrons moving so fast thermally? You should be able to capture that in one sentence. And I want to see if you can come up with that sentence. Say again? Waves. So if I am your 12, 15 years or 14-year-old nephew, would that... No, that's okay. You tried. I give you credit for trying. That always is better than not trying. You're ahead of all the people who didn't try.
They don't always move straight.
They don't move straight. How does that make them go fast? I mean, I'm trying to explain why they go so fast. Why 200,000 miles per hour?
Because compared to their mass, the force that's acting on them is extremely huge.
Right. Compared to their mass was the key part. Because if they're extremely light, so to have a certain energy, they have to go super fast. It's because they're very, very light. It's because of this. This is what caused this number being very small, right? This. Now, if I wanted to, now you want to say, oh, by the way, but no, when you see, you know, this light turns on, you know, there's current flowing through here and all this thing. But the electrons, the whole of all of these guys moving around fast, but they are slowly moving laterally. drifting. And that's very slow. How would you explain that in one sentence?
So like there's like a cloud of electron at the beginning and at the end. So
Right.
when they move, like they actually move together.
So you say the cloud moves together, but that doesn't explain why the speed is so small. Yes, in the back and then in the front. There's a lot of them. Right. There's a whole bunch of them. So when you have a whole bunch of them, they don't need to move that fast. Even if they each one of them moves a tiny bit, that results in a fair amount of movement of charge. So that's the way to think about it, to capture. But anyway, so that's physics. That's the physics of it, right? But now, from that physics, you come up with something. So we realize that because of that rescattering, and you can write this more formally and mathematically and all those things, you will see that as long as your electric field is not too large, as long as your voltage is not too large, then what happens is that you can write that proportionality between the velocity and the velocity is proportional. Let me just stay here for a second. We will see that inside that lattice, the velocity of movement, we drift, is proportional to the electric field, not the acceleration. And that proportionality constant is shown with the quantity that you will see later on when you talk about semiconductor physics, which is called mobility. This is what mobility is. And again, this is not, we are not going to go any deeper in the physics of it, but you will see it somewhere else. But here's the thing. So once you have that relationship, then your resistance, your current, your voltage becomes proportional to your current. Or your current likewise becomes proportional to your voltage, where G, which is called the conductance, is defined as 1 over R. Right? And that's Ohm's law. But you can see it comes under certain conditions. Now, let me ask you this question. So if I do an IV characteristic, or more precisely, let's say let me do a IV characteristic instead of a VI characteristic. So an ideal resistor looks like what? What does an ideal resistor look like? It's a straight line, right? And what's the slope of this line? It's, well, the way I've drawn it's 1 over R. So I'll show it this way. Though that's the way we show slopes, right? So it's 1 over R. You can write it as G or 1 over R. So that's an ideal resistor, but that's a mathematical abstraction again. Generally, a resistor is this. I is, you can write it as a function of V, or V is a function of I. And this can be also a function of time and other things too. So here's what's going to happen. So if I take an actual resistor, if I go to the stock room today and take an actual resistor and bring it here and apply a voltage, start applying a small voltage. Let's say I take a, 100 ohm resistor and start applying voltages. Like 1 volt, 2 volts, what's going to happen? If you do that, you will see that initially, as you increase the voltage, the current goes up linearly according to this. It may be a little bit off because it may say 100 ohm, 100 ohm, but maybe actually 98 ohms, or maybe 103 ohms. There's some tolerance and variations on this. So that's what's going to happen. But then after a while, if you keep increasing the voltage, I will see something like this happening. So what's happening there? Guesses. Let's say I'm showing you an experimental result. Yes? Yeah. For example, it could be heating up. The resistance it could be increasing depending on what kind of resistor it is. Some resistors increase with temperature. Some of them actually decrease. But the ones that you get from the stockroom, you are right. I mean, they would be decreasing. So that's what's going to happen. So I keep doing this. I could keep doing this, and then I see this. What happened there? Yeah, it melted or something like that. And I am persistent. I say, well, I'm curious. I want to see what happens. I keep going up there, and then all of a sudden it just jumps up. What happened there? Say again? Avalanche of what? No. Yeah. Go ahead. Yeah. Breakdown of what? I mean, it's already melted. Yeah. Okay. So it's breakdown of the dielectric. It has a name. It's called arcing, right? But it's the breakdown of the dielectric. Yes. It's not avalanche breakdown is something else. It happens in diodes and all those things. So let's not confuse those two things. It's dielectric breakdown. Air breaks down. So you have arcing. It's spectacular. You can do welding and things of that sort. So then I keep going in this direction, so I'm keeping going in this direction, right? And then it jumps up. And then when I start lowering the voltage, what's going to happen? Start lowering the voltage. I said, okay, well, exciting. I'm done with this. I got to go home. I see that, okay, it actually keeps going down a little bit and then drops down and stays here. And when I come back here, that's what's going to happen. This is what a real resistor will do if you apply an unlimited, mathematically unlimited voltage. And probably even if you go beyond that, there are some other interesting physical things that may happen at some point to you. Now, that's a contrast with what Ohm's law says, which is basically looking at it here. So Ohm's law is an empirical physics-based law in a limited range of operation from a physics standpoint. From a mathematical standpoint, it's just a mathematical proportionality. But not all things are that way. There are lots of different things. So now let's say if that were true, so we'll talk a little bit about what happens when these things are true, and then we'll come back and talk about other kinds of variations that you may have. So going through this rather quickly, so what's the power? What's the power that's delivered to a resistor if you have a certain current and a certain voltage? So what's the power delivered to a resistor if you have I and V across the resistor? I times V, right? But now we have a relationship between I and V. Right? So you can write I in terms of V or V in terms of I. So if you write V in terms of I, you get R I squared. And if you write V in terms of I in terms of V, you get V squared over R. Or you could conversely write it as I squared over G or G V squared. You should also get comfortable with conductance, because you will see that it would be useful in a lot of situations when we write Y matrices and all those things. And again, from this simple relationship and KVL, for example, you can see what the equivalent resistance of a chain of resistors is going to be R1, R2, R2 all the way to Rn. You can easily show that if there's a current I flowing through them, the voltage drop across the first one is going to be R1I plus R2I all the way to Rni. So this is the voltage, which is equivalent to R1 plus R2 all the way to Rni, which would be equivalent to R equivalent Ri. So the equivalent resistance of this thing would be the sum when they are in series. And when they are in parallel, again, you can very easily show, and we are going to show it very easily, that if you have n resistors in parallel, except for the fact that I'm running out of space, what is common among these n resistors in parallel? The same voltage. So they have the same voltage, so I can write it the other way around. I can write it as the sum of but the current is the sum of all the currents. So I can say I total is I1 plus I2 all the way to In, which is going to be voltage divided by R1, voltage divided by R2, all the way to voltage divided by Rn, which by factoring voltage results in an R equivalent, 1 over R equivalent. That's going to be 1 over R1 plus 1 over R2. And if I write it more cleanly here before I make it microscopic, is that 1 over R equivalent is going to be the sum of 1 over Ri's. Or conversely, you can write it as G equivalent being equal to the sum of G's. When you have parallel things, conductances are easier to deal with. Right? These are the things that you should be familiar with. We are just arriving at them from this perspective. Okay, so that's for that. Any questions? No? Okay, let's move here. Okay, but resistors in general do not have to be linear. We saw that in the physical sense, they are not linear. They're not necessarily linear, and that basically is fine. So, for example, if you have an IV characteristic, you can have a nonlinear behavior. You can have something that looks like that, and we'll see examples of that. We'll actually use examples of that. Now, if it's nonlinear, that's fine. You can write it I as a function of V. If it's this kind of nonlinearity, we call them actually memoryless nonlinearity. If it's something that doesn't depend on the past and it doesn't change with time, it's a memoryless time invariant nonlinearity. But it doesn't even have to be that way. It can actually be time varying. It can be something that moves around, and we'll talk about that in a minute. But an example of a nonlinearity, a nonlinear resistor, is a diode, a p-n junction diode. Now, a p-n junction diode, this is the symbol for it, is made out of two pieces of semiconductor. And again, we are not going to go into the physics of it. It's very interesting physics. But it basically is an IV characteristic that's defined by an exponential. So I diode is essentially some IS constant exponential of V over Vt plus some constant, but let's just make it simple. So Vt is some quantity, it's Kt over Q. Again, you don't need to remember these details now. You'll learn them in more detail later. So which has room temperature is about 26 millivolts. Now, if you plot this quantity on an IV characteristic, it's an exponential, right? So it will look like this. Something like that. Now, this is what a realistic diode behavior looks like. But in practice, we want to, again, would like to abstract things. We would like to simplify them. We want to create models that are simple enough that we can deal with, and then build up upon those. Build it up using those, and make it as complicated as we need to, as opposed to as complicated as it is. So what is the simplest abstraction of this thing? You can see this is useful because at least current flows in this direction mostly, and very little current, at least based on this equation, no current, but there's very little current that flows in the other direction, flows in the opposite direction. So what's an idealization of this thing that you can think of? If I want to define the ideal diode, which would be, obviously this is a diode is really a nonlinear resistor, right? You can see. It can be defined by a nonlinear curve. So what's an ideal diode? If I wanted to idealize it as much as I can. Yes?
Voltage source on that graph, so just like a straight line up and down the current. Right?
Where? At what point?
Like at a specified voltage.
Okay. Since I'm trying to abstract the heck out of it, right? I would put it, that's a good way of thinking about it, but I put it at 0. Would I go in both directions? Would this work?
No, it wouldn't be negative.
Right, okay, so only for the positive half, right? Because you're trying to capture this. I'm just going to abstract the heck out of it, as I said. All right, so but that's not the whole thing, because that doesn't show the full functionality. What happens if the voltage, what happens here? How do we capture this part of it? So you have a current source of 0 value, essentially. So this is an open circuit, right? This half is an open circuit, and this half is a short circuit. So it's a short circuit here and an open circuit here. This is really as ideal as you can make it. So it's the perfect one-way valve or something. So anything that comes in this direction, if there's any current flowing in this direction, it will let it go with no resistance. It's 0 resistance, it's a short circuit. And anything that wants to go in the opposite direction is completely blocked. It becomes an open circuit. This is the ideal diode, right? It doesn't get any more ideal than that without losing its diodeness, right? So now if we start with this ideal diode, how do we generate things that look more and more like this? So for example, I want to create some sort of a slope. It doesn't have to be nonlinear. Let's say but I want to have something that has some slope. So let's say I start with this ideal diode. Yes, add a resistor, as you pointed out. Now if I add a resistor, this becomes what? So let's just add the resistor. And once I add the resistor, what is it going to look like? I have a resistance in series with an open circuit. What is it? An open circuit in series with some resistance. What is it? Open circuit still, right? Does it make sense? I have an open circuit in series with something else that's not open circuit. It's open circuit. So on this side, it's not going to be affected. How about here? I have for this side, I have a resistor in series with a short circuit. What is that thing? The resistor itself, right? So whatever that resistance is, you're going to get its slope. So let's call this R. So I can make it now a little bit more realistic. Now, what if I want to create some sort of a threshold? Say, well, look, you know what? If I wanted to idealize this, I would think that this is probably something like that. A line like that, that green line would be probably a good approximation of that. If I want to give it an offset, it's called the threshold. How would I do that? Using the idealized things that we've created. Now, we've broken it down to the basic core essentials, right? So now we have these Lego blocks that are very simple blocks, and we can put them together. Yeah, voltage source. So I can put a voltage source here of some value V, let's say V1. And what does that do to this plot? If the current could flow for a voltage here, now I have to apply this much more across this so that I see that voltage across here, right? Does that make sense, what I just said? I'm going to say it again. So assume that the voltage source was not here. So to produce a certain point in this curve, you need to apply a certain voltage, right? Now that this voltage is also in series, you need to apply this much more to get to that point across these two, right? So it shifts this here to the right. So once I add that other voltage source element, the curve becomes like that, and this becomes that V1. And that's still the same slope. So you can see that you can make it more and more complicated. This is not where you don't have to stop here. You can continue making it more sophisticated. In fact, you can use this to produce certain kinds of IV characteristics, of desirable IV characteristics. So for example, let's think about this. If I take one of these and put another one of, so let's take one of these branches. And I take another one just like that, put it next to it, except for the fact that, let's say, well, let's give it some numbers. So let's say this is 1 ohm, this is 1 volt, this is 1 ohm, this is 2 volts. What is the IV characteristic of these things going to be? Well, this I is going to be sum of I1 and I2. So you get two curves for each one of them, right? You get a curve for each one. So you get, for this one alone, if the other guy was not here, what is the IV characteristic like? What is it like? Kind of like that, right? So it's a 1 volt threshold, so it comes to 1 volt, and then at 1 volt it goes with a slope of 1. Right? Make sense? This is what this part only would have done. Right? You don't look convinced, some of you. Or is it just not that you're not comfortable with it yet? Okay. So let's play a little bit more with it. Maybe we get a little bit more comfortable. So now, how about this side? If I just had this guy by itself, this branch, what would that do? How would that look like? It looks like this one, except for the fact that it happens at 2 volts, right? So the current through that branch follows this red curve. So you come to 2 volts, and you go with a slope of 1. So what is the total current through this branch, which is the sum of these two currents, right? It's the sum of these two curves. Do you agree? So it would be something like this, where the slope becomes 2 here. Oh, yeah, it becomes 2. And it's 1 here. So I could make it more sophisticated response out of these. What if I wanted to make something a little bit more, a little bit different? So let's say, if I say, okay, I'm trying to construct something. So this is now becoming a design problem. And you will give you some design problems. So if I give you, say, well, okay, you know what? I'm trying to construct something that does this. I need it for my guitar amplifier. I want to create this kind of distortion. I want this to be 2 to 1. I want it to happen at 2 volts. I want this to happen at -1. And I want the slope to be 1 to 1. How will we construct that? Now this is becoming a design problem. Can you think of a way of constructing this? Well, we know how to construct this side of it, hopefully by now, right? At least we should have some idea. The more you play with it, the more you get comfortable with it. How about this side? What if I need something that does just that, right? How would you do that? Yes. So I want to forget about this side for now. Let's assume that I want to generate something that's flat and goes down like this. What would that look like? I want everyone to think for a second before we answer it. It's made out of the same components. I just needed to do some variations on those. You want this transition to happen on the other side. So what do you need to do what is responsible for this transition? It's this guy, right? You put it upside down. So if I put it upside down, put a resistor like this, and put an upside down voltage, this will produce something like that. And then I can put that in parallel with one of these guys, and I can get that part. And the current being the sum of those two things, you will get the overall response that you were looking for. So this is what other second branch gives you. And you can I could in principle give you something a little bit more sophisticated, more complicated, right? I could try to, you can see once you break it down to the core elements, and once you understand something, it's like playing with Legos, then you can construct. And that's the objective of engineering. So all of these things are tools that enable you eventually to build and design. So if I gave you something like this, say I need an IV characteristic that looks like this. So it says IV. I want you to make an IV characteristic for me that looks like this. It goes up at a slope of 1 and then switches to a slope of 2 at 1 volt and 2 volts. And the slope is 1 here, and the slope is 3 here. And it goes down to negative 2 volts, and it drops down at this rate of 1 first, and then it goes down to the slope of 2. And I want something that looks like that, an IV characteristic. And if I ask you right off the bat how many branches that is, what would you tell me? If I wanted to make 4 branches, right? And you can, as an exercise to yourself, do that. There will be 2 branches in the forward direction, 2 branches in the reverse direction, and so on and so forth. Does that make sense? All right. Okay, let me, let's spend a couple minutes on something. Let's finish a subject so next time we can start at a good point, just like 2 or 3 minutes. Now, we talked about nonlinearity, right? These are examples of nonlinearity. But there's another example, which is an important one. It's the time-varying systems. What is a time-varying resistor? So time-varying resistor or time-varying system. So what does it mean in that IV curve? So let's say, for example, you can have a linear time-varying resistor. What does that mean? It means that this line, the slope of this line is changing with time. So it can switch back and forth with time. How can you make something like that, something that changes with time, a resistor that changes with time? A simple example is that let's say you have a resistor, a variable resistor, right? And you attach this to a mechanical mass and spring and attach it to something, and then you start letting this go up and down, right? Right? It just moves up and down, and it's a time-varying resistor, right? I mean, the resistance between this, well, not that node, but from this node and that node, this is a time-varying resistor that changes with time. Another example, you can think about even time-varying components in general. So you can have a time-varying capacitor. You can have a parallel plate capacitor, right? So it has electrical connections. But then this terminal is also attached to a handle. You come here and grab this handle and start moving it up and down. This capacitance is changing with time. Now, in fact, let's say I'm applying some AC signal here. If I do it in the right phase, I can make the capacitor smaller at some point and make it larger at other point. And when I do that, if I do it at the right time, I can do it so that I do work on the capacitor, right? When I do work on the capacitor, what happens? I put energy into it, you can actually make the energy of this capacitance go up. This is called parametric amplification. This is actually something that's actually is used. It's called parametric amplification. And you can do that by pumping it. Essentially, I'm pumping it. Now, but from the capacitor's perspective, if I say, okay, I'm just an electrical engineer, I don't want to think about anything else, and if I draw my line around here, I have a time-varying capacitor, right? I have a capacitance that's a function of time. And as such, it's not conserving energy, right? Because I am pumping it from outside. Mechanically, I'm putting energy into it, but it's converted to electrical energy. But from a purely electrical perspective, it looks like something that doesn't conserve energy, because the energy is increasing. You remember we said the conservation of energy comes from symmetry of time or homogeneity of time. This is an example. When something becomes time variant, it doesn't have to conserve energy. Now you may say, well, wait a second. We haven't violated the conservation of energy. The energy is coming from a different domain, but within the electrical domain, it's not conserved because it's time varying, for example. There are other ways to make it non-conserved, but this is one way. So that's basically what I wanted to talk about. And then there's, so these are different kinds of resistors that you can have. So let me just stop here. And what happens is that